All right, let's check out part C. So we have a cubic term at the top and a fourth order term in the bottom. It doesn't look like, when you first glance through that, it doesn't look like that you have the sum of the squares or the difference of the squares. But somehow, like, we have to see that if you want to go in that direction of using trig substitutions. So I'm gonna go with rewriting the bottom because the bottom looks like it's a perfect square of um, x squared plus 1. Okay, that's our first observation. And the second observation is that um, if you look at the bottom, that's a fourth order term, right? Fourth order polynomial. If you take the derivative of that, you get some part of that popping at the top. So let me just show you how I can see that. So I have x cubed plus x and x to the fourth plus 2x squared plus 1. That's one part of the integral, right? And then I have the other part of the integral, so it's dx, 1 dx divided by x to the fourth 2x squared plus 1. In fact, let me just also convert the bottoms. For this one I won't. Let me just put that back. But for this one, I'm going to write that as like quantity squared, okay? Okay, so the first integral is a very good U substitution problem because the derivative of the bottom pops at the top. And I'll explain in a sec. For the second one, well, we will definitely use a trig substitution because otherwise you can't integrate that with the techniques that you know. Or it could be very hard to do it. Okay? So two different integrals to handle. All right, so for the first integral, as I said, I'm going to write here what the U substitution looks like. Okay? I'm going to call the bottom to be U. Okay? So du is 4x cubed plus 4x dx. And if I pull out 4, okay, this is exactly what you have here. 4 times x cubed plus 1, x cubed plus x, I'm sorry, it's a typo, right? So this way, you see x cubed plus x pops in the top here. So that together with dx is going to be my du. So in turn, this integral would look like du over u. Let me just write that, in fact. So this integral is nothing but 1/4 du over u because we have to also factor this, right? This 4 over there. So x cubed plus x dx is 1/4 du, and now we have du over u. So this integral is taken care of already. Okay, I'll integrate that in the next step once I'm done with this integral. So now for this one, I'm going to use a trig substitution. Okay, so I'm going to use a different color here. So why don't we use x equals tan theta? Okay, because a is 1, right? This is 1 squared. So x squared plus a squared. So it's a tangent theta in the formula. So it's x tangent theta. So that dx is going to be secant squared theta d theta. Okay? And I'm going to put the triangle right here after I erase this. I'm going to put the triangle right here. Okay? That tan is opposite divided by adjacent, and it's x already. Tan theta equals x, so x over 1. So the hypotenuse is going to be sum of the squares, radical sum of the squares. So 1 plus x squared. Okay, I think we have all the ingredients. Let's also write what x squared plus 1 is. So that is tan squared plus 1. And by using the Pythagorean theorem, that is secant squared theta. Okay? All right, so again, we have everything to convert this integral into the theta version of that. So we have 1 dx, so dx is secant squared theta d theta. And then you have x squared plus 1, quantity squared, that is secant to the fourth theta. Okay? So let's simplify this. So we have d theta over secant squared theta. Okay. And the good news is that secant squared is 1 over cosine squared, because secant is the reciprocal of cosine. So why don't we flip that over so that the second integral is nothing but cosine squared theta d theta. Okay. So now I'm gonna integrate the first integral and the second integral. But before I do that, pay attention to cosine squared theta. Whenever we have even powers of sine or cosine, we remember that we rely on to the power reducing formulas. Okay, so in other words, this cosine squared theta equals cosine 2 theta plus 1 over 2. Just keep that in mind, and you can check the power reducing formulas if you can pause the video now. Okay. So now both integrals are integrable by using the known techniques, and let's write that down. Okay. So this is equal to 1/4 ln absolute value of u. Okay. And then this is 1/4 sine 2 theta plus theta over 2 plus c. Okay, so I did one by one integration. So all we need to do now is to go back to the original variable. So you have to do back substitution. Okay, so let me just copy everything down in the next slide, and I'll just use back substitution one by one. All right, so I just copied everything down here, and I also copied down the substitutions that I used along the way. All right, so x equals tan theta. Since I need theta by itself here, so I also need to convert this into arctan x, or tan inverse x, whichever you want to call it. Okay, and also I have sine 2 theta here, so why don't we use the double angle formula for that purpose, because we will also go back to the triangle to simplify that. Okay, there we go. If you use the double angle formula for sine 2 theta, that's 2 times sine theta cosine theta. Okay, let's try to back substitute now. 1/4 ln u, and that is ln of x squared plus 1 squared. That's already positive, so we don't need to put the absolute value sign here. Let me just clean that. So x squared plus 1 squared. I have 1/2. Now let's go back to the triangle. I need sine theta and cosine theta. Okay, so here, if you look at that triangle over there, sine is x over radical 1 plus x squared. Cosine is 1 over that. So 1 is x over that. And the other one is 1 over that. Okay, that takes care of the second term over there, plus theta over 2. So plus theta 1/2 tan inverse x plus c. Okay, let's simplify further. By using the ln property, I can pull this out. So that makes the outside number to be 1/2. Plus x over 2, 1 plus x squared, plus 1/2 tan inverse of x. And I think we are completely done. All right. So this takes care of part C. We have one more question to go. I'll meet you in the next video. All right, bye.